Hello, my name is Michael Langford, and I am presenting a paper titled Know What You Know, Predicting Behavior for Learning-Enabled Systems When Facing Uncertainty. This paper has been co-authored by Dr. Cheng and based on research conducted at Michigan State University. Our research has been focused on learning-enabled systems, where an LES is any system with functionality that is defined by training experience. For example, an autonomous vehicle can include machine learning components for object detection, path planning, etc. These systems have shown a lot of promise in controlled environments, but there are problems that must be addressed when we begin to deploy these systems into the real world. The real world is vast and full of corner cases, and any claims about the accuracy of a learning system on validation data at design time can become meaningless when runtime conditions differ drastically from training and validation data. And this is a significant problem for safety critical applications where we require some confidence that fail-safes will be in place for all potential hazards. Safety critical LESs need to account for unexpected or untrained conditions. And so we ask ourselves, how can we determine when an LES has encountered phenomena outside of its comfort zone? For this work, we focused on deep learning systems, or deep neural networks. These are data-driven and trained under supervision with labeled training examples, where we adjust the DNN weights to minimize the error for the provided examples. There are certainly many benefits for including DNNs into software systems. They can lead to solutions for complex tasks that would otherwise require significant human effort. However, they do require a large amount of data as a substitute for domain expertise, which can lead to a number of challenges. DNNs can be very sensitive to data bias and data quality, otherwise known as the garbage in and garbage out problem. And they can also be sensitive to superficial patterns in the training data. For example, a DNN might decide an image contains a cat simply because of a cloud in the sky that's in all of its training images of cats. And there's also been a large amount of research in generating adversarial examples that can deceive DNNs in unexpected ways. Ultimately, what we'd like to do is make DNNs more robust and more generalizable, or more capable of handling data outside of their training distribution. To help address these problems, we propose a framework for predicting performance boundaries of a DNN to assess how it will behave when facing uncertain conditions. So we've introduced the concept of a behavior oracle demonstrated on a camera-based object detector. The object detector is a DNN that locates and classifies objects within an image, such as cars and pedestrians in this example, where the objects are labeled with boxes to show their location and the type of object. And we've trained an object detector that achieves 88% recall on validation data. However, a majority of the training and validation images have been taken in clear, sunny weather. What we'd like to know is how the object detector will respond to other weather conditions or phenomena, such as a raindrop falling onto the lens in this example. We call these types of phenomena known unknowns because we know how to describe the appearance of the phenomena, but we don't know how the object detector will respond to the phenomena. So for this work, we look into how we can create a behavior oracle that can identify the known unknown phenomena and predict how the DNN will respond to the phenomena. To accomplish this, we've created Enlil, named after a Sumerian god, who's the keeper of the Tablet of Destinies. In this case, Enlil is a software framework we've developed to automatically assess LESs under simulation and then construct a predictive behavior model to determine the destiny of the LES or how the LES will behave based on Enlil's observations. So for example, if we use Enlil to create a behavior oracle for the object detector and we provide it an image with rainfall, the behavior oracle will output two things. First, it will output a perceived context to describe the rainfall, and then it will output an inferred behavior category to describe how the object detector will respond. And in this example, it perceives the angle, density, and intensity of the rainfall as a sort of counterexample, and it also predicts the object detector will fail to detect objects under this specific context of the rainfall. Before using an allele, we must first define a set of behavior categories, where a category can be based on any observable metric of the system under test. So for this object detector example, we might look at the object detection recall as a behavior metric, and then we can measure the difference in recall for a set of validation images taken in clear weather versus when we introduce a specific example of a known unknown phenomena, like a raindrop, rainfall, etc. Then we can define different behavior categories based on the difference in recall. So for example, we might have 3 different behavior categories where category 0 is any phenomena that leads to 5% or less difference in recall. Category 1 leads to up to 10% difference in recall, and category 2 leads to anything over 10% difference in recall. A key note here is that these behavior categories are based on statistical metrics of the validation data rather than basing a category on how a specific raindrop affects a specific image. We're choosing a category based on how a specific raindrop affects multiple images. The NLIL framework is divided into 2 stages, where the first stage is responsible for generating a large collection of examples, or an archive, that leads to each behavior category. We call this context generation because we're generating different contexts of each known unknown phenomena. And here's an example of how we evaluate a single context. Again, our object detector is given a set of validation images taken in clear weather, and we achieve 88% recall. Then we can apply a single context of a raindrop with the shown attributes, blur, radius, and position, and then we apply that raindrop to each validation image, and as shown here, and in these images we get 53% recall. So this specific raindrop is assigned behavior category 2. So to get from a single context to many contexts for each behavior category, we take advantage of evolution. And we harness evolution to generate many relevant contexts for each behavior category. Using evolutionary computation, NLIL creates an archive for each behavior category, evolving each archive in parallel. And populations are evolved to create diverse examples of the simulated phenomena using novelty search. Then we filter and migrate individuals at each generation into the respective behavior category based on what NLIL observes during its automatic assessments. To illustrate, we start at generation 1, where each point here corresponds to a different raindrop example. The X and Y axes on the bottom correspond to the relative position of a raindrop in the image. The Z-axis corresponds to the recall observed when we apply the raindrop. The colors correspond to each behavior category, where green is category 0, yellow is 1, and red is 2. At the first iteration, we find mostly category 0 raindrops, implying that most raindrops are not a challenge for the object detector, and a random selection is not likely to uncover a problematic raindrop. In fact, in this case, we only have one problem raindrop in the middle of the image. At generation 2, NLIL is able to evolve more examples for category 1 and 2. And then finally, at generation 6, we produce an equal number of diverse examples for each behavior category, showing a nice coverage of the raindrop space. So a key takeaway here is that NLIL uses novelty search with parallel evolution to create diverse examples for each behavior category efficiently. The next step is that we want to take advantage of these behavior archives to help classify a behavior category for any given raindrop. So to illustrate, if we're given this specific image of a raindrop and this set of behavior archives, which may or may not include this raindrop example, we want to be able to map this raindrop to a point in this space and one of the observed behavior categories. For the second stage of NLIL, we construct a behavior model of the LES using model inference. Here we construct a behavior oracle as a separate DNN that can perceive a context of the introduced phenomena and infer a behavior category for the learning-enabled system. The behavior oracle DNN is composed of multiple subnetworks with different subtasks. In our example, the behavior oracle is given the same image as the object detector, and the first subnetwork is responsible for isolating the interfering phenomena. In this case, that's the raindrop. Using a series of convolution layers, this subnetwork outputs an image of the isolated interference. Next, a feature extraction subnetwork reduces the given interference image into a numeric vector of learned latent features. And this feature vector is given to a context regression subnetwork that basically translates the feature vector into the attributes that we use to describe the raindrop, such as the position, the radius, the blur, etc. This is our perceived context of the raindrop. And then finally, a behavior classification subnetwork predicts a behavior category based on the perceived raindrop attributes. That's our inferred behavior of the learning-enabled system. So as a whole, this behavior oracle DNN is trained based on the examples and the observed behavior categories stored in our behavior archives, such that it can take any image with a raindrop and output both a perceived context and an inferred behavior category for our object detector. To help demonstrate how we can use these behavior oracles, I have a few examples to show. Here we're given a clear image of a van driving in front of us, and our object detector is able to successfully detect every vehicle in this image. When we apply a light pattern of rainfall, we don't know how the object detector will respond to this because our validation data doesn't contain any examples of rainfall. And in fact, in this case, the object detector can detect every vehicle still with this pattern of rainfall. But again, we don't know that beforehand. When we process that image with our behavior oracle, it can correctly infer that the behavior category will be 0, which means that it predicts that there will be little impact on object detection. So in this case, the behavior category correctly identifies that this pattern of rainfall is not a problem for our object detector. Now we'd like to see what would happen when we apply this heavy pattern of rainfall. And in this case, the object detector fails to see the van in front, and that's obviously a problem. And that's something we would never know because our validation images do not contain examples of rainfall. But when we process that same image with our behavior oracle, it correctly infers that the behavior category will be 2, which means that it predicts that there will be significant impact on object detection performance. To further demonstrate, I have some examples of simulated raindrops on a camera lens. And since the behavior oracle also outputs a perceived context of the introduced phenomena, this can help inform systems on how to identify the source of interference. So for example, here we have 2 different raindrops where the one on top is smaller than the one on bottom. And these images show how these raindrops impact object detection. So the one on bottom obviously has a larger impact because it's larger and more towards the center of the scene. And when we process these images with our behavior oracle, the one on top gets categorized as a category 1, which means that it's predicted to have moderate impact, but the one on bottom is predicted to be category 2, meaning that it is predicted to have significant impact on object detection. So the behavior oracle can both locate these raindrops and correctly classify their behavior categories. Finally, we have a video to demonstrate how this system can operate in real time, where we have, again, an image of parked vehicles, and the object detector can detect all of the cars. But here we start simulating raindrops, and as the raindrop increases in size, it starts interfering with the object detection. Then we can take the raindrop away, and once it's away, then we can turn on our behavior oracle and then do the same. And you'll see that as the raindrop gets larger, it starts getting classified as category 1 and then category 2. And then we can take the raindrop away and it will correctly classify category 1 and then category 0. So here we're showing the object detector can operate at runtime to perform these behavior classifications. To summarize, software engineering for learning-enabled systems is challenging, and methods are needed to self-assess learned behavior. So we've introduced NLIL as a framework for creating these behavior oracles that can perceive known and unknown phenomena and infer behavior categories for learning components. In future work, we want to look into ways to integrate NLIL into an autonomous rover, explore different sensor inputs, and alternative behavior categorizations. Again, my name is Michael Langford, and thank you for listening to this presentation.